This is APAB. We are doing section 2.6, which is related rates. So I know this piece of paper is tiny. We're going to address that in a minute. I know it's frustrating if you can't see it. You will also have this piece of paper either on my website or on Google Classroom or on any number, or handed to you in person, or like any number of different ways. So if this is looking tiny, that's okay. We're going to walk through it, but also I'll make sure you have a copy of it. So fundamentally, related rates are disproportionately word problems. So I know some of you are cursing either under your breath or out loud the moment I say that, because we are doing a lot of word problems in these videos, friends. I pre-printed so that we would have access to word problems so I wouldn't have to write them all. So when we look at a related rates problem, it is quite simply a problem where there are multiple things changing, hence rates, and those rates are related. For example, if I'm blowing up a balloon, right, the rate at which I blow air, right, that's volume, it's a volume of air, into the balloon, right, the rate at which I'm blowing air into the balloon is going to affect the radius of the balloon, right? As I blow air into the balloon gets larger and its radius grows. So the rate at which I'm blowing, which would be the volume, right, so that would be what we would call dv dt, the rate of change of the volume, dv, over the rate of change of time, dt. That is going to have some relationship to the rate of change of the radius with respect to time, so probably dr dt. That's all related rates are. So let's walk through what the steps to solve a related rates problem are, and then we're just going to do a ton of them. I have E1, P1 up to E7, P7, all different types of problems, and we're just going to practice a lot. So years ago, somewhere on the interwebs, I saw some math teacher, much smarter than I am, use the term dreads as a way to solve related rates. So, and you'll notice that my version is dreadsa, sort of like Leviosa, channeling our inner Hermione. So dreads is just a sort of a way to calm down when you see these word problems and think, okay, there are logical steps to solve them. They're not steps that are set in stone, in the sense that each one of the steps is going to require you to apply some knowledge that you have previously, whether it's algebra or geometry or whatever, but it's a good way to kind of guide you as you get a little lost during these problems. So let's walk through what dreadsa is, okay? And again, if you can't read it, don't panic. You're going to have a copy of this. I'll probably see if I can even just link one to the video. So what's the letter stand for? So the first D in dreadsa is diagram. And the D and the R in dreadsa really go together. So the D and the R are kind of one step. The first thing you want to do is draw a diagram of the situation. Now, there are a few cases where that's not worth it, but most of the time these are going to be situations that visually make a lot more sense if you draw them. So, for example, so you're going to draw a diagram. Every once in a while it's provided, which is awesome. You're going to label the values you have on your diagram either with variables or constants that you know. You don't want to put numbers on your diagrams unless they're constant throughout the problem. For example, when a 25-foot ladder is sliding down a wall, the length of the ladder is constant, it's 25 feet, but how high it sits up on the wall would have to be a variable because the ladder is sliding down the wall. How far the ladder sits from the base of the wall has to be a variable because the ladder is sliding, so that's moving, okay? So those would be variables. And then the R in dreadsa is rates. You're also going to label rates on your diagram that you know. Note that these rates are generally the variable you assigned in your diagram, dt. So for instance, if you used h for the height of the ladder that I just mentioned, you would have dh dt. If you used b for how far the ladder was out from the base of the wall, then that would be db dt, right? Also note that rates are positive when the variable is increasing in value and negative when the variable is decreasing in value. So for instance, if h was the height of a ladder on a wall, as the ladder slides down the wall, h is getting smaller because the ladder's sliding down, right? It's not the down that makes h negative. It's that or dh dt negative. It's that h is physically getting smaller since h is the height up the wall of the ladder. Let's see. E in dreadsa, equation. So you're going to write an equation relating the variables in your problem. Often, you want this equation to be two variables, even though the basic equation you need has more than two variables. We're going to deal with that in a little bit, but most of the time these equations that you're picking are going to be equations that you have known since like maybe before high school. They're going to be things like Pythagorean theorem. It's going to be things like maybe SOHCAHTOA. It might be the area of a triangle. They're not going to be really hard formulae. They're going to be stuff that usually, if you didn't know before high school, you knew by basic geometry. So the formula is not usually, like the equation you're going to use is usually a formula that you are familiar with. A lot of the time it's Pythagorean theorem, to be perfectly honest. The second D in DREDSA is derive. So you're going to differentiate, you're going to take the derivative of that equation with respect to t, usually, because it's usually dt. And S is substitute specific stuff, because I'm super alliterative. So basically you're going to plug in values that you know that you couldn't put on your diagram because they were time specific, right? The ladder might be 25 feet long, but we might want to know the rate as it's changing when the ladder is 10 feet from the ground. Well, that would be h is 10, right? So that's stuff that's specific to a time. And then the A that I tacked onto the end is answer the blasted question with units if applicable. Sometimes we do all this work and then we forget to answer the question that is asked, and boy does that feel frustrating. So after that little intro, we're going to go ahead and just dive right into examples because that's the best thing that we can do here. So I'll put this off to the side. I know it's tiny and you probably can't read it anyway, but I'll put it there. So I think these are big enough that you should be able to read them, hopefully. So I did E1 and P1 on the same paper, and then we'll do E2 and P2 on the same paper. And this is mostly just so I don't have to write the ridiculously long word problems on my whiteboard. So let's go ahead and walk through DREDSA with example 1. Like I said, we have up through E7, P7, so we're just going to do a lot of math. I'll stop the video probably after the first couple examples and then do another video. Okay, E1. A ladder 25 feet long is leaning against a wall. If the lower end of the ladder is pulled away from the wall at a rate of 1 foot per second, at what rate is the other end slipping down the wall when it is 24 feet from the ground? Okay, so let's go ahead and start with E1 with our diagram. Okay, it doesn't matter which way you draw your wall. Okay, so this is going to be my wall. You can assume that the ground is horizontal and that walls are vertical unless you are specifically told otherwise. And most of the time in calculus, they'll be nice, happy things. So I'm going to go ahead and assume that the ground is 90 degrees with the wall. And I have some ladder up here. Okay, so I know the ladder is 25 feet. That's a constant, and I can label it on my diagram because of that. I know that the top of the ladder is sliding down and that the bottom of the ladder is sliding out away from the wall. So this is my diagram. I'm going to do my diagram and my rates. Now remember, on my diagram, I need to label the unknown quantities that are changing with a variable. So I don't know how high the ladder reaches up the wall. I'm going to call that quantity y. You could use h if you wanted. I'm going to use y. I also don't know how far the ladder sits out from the wall, and I'm going to call that x. Now that I've labeled my variables, I can label my rates. I was told that the bottom end of the ladder, this spot right here, is being pulled away from the wall at 1 foot per second. That means that x is changing with respect to time, so dx dt, at a rate of 1. And you can write 1 foot per second if you want, or just 1, it's up to you. We're going to need the units at the end, but I'm not a science teacher. I definitely let you get away with not using them until the end, as long as you know the right units. Notice that it's positive not because I'm moving to the right, but because x is getting physically longer. This is the rate of change. This is the rate of change of the thing I called x. As this problem moves, x will physically get longer because, like, as the problem's happening, what's going to happen is that x is going to get longer and y is going to get shorter. Okay, so I've now got my diagram and my rates. The next thing I need is an equation that relates the variables I have and any other quantities I have. And I'm pretty sure that that equation is Pythagorean theorem, right? I think x squared plus y squared should be 25 squared. So x squared plus y squared is 25 squared. Now I need to differentiate with respect to t, and this is where 2.5 comes into play when we learned how to do implicit differentiation. Remember that in 2.5 we were differentiating with respect to x. So anytime we differentiated anything that wasn't an x, we had to use the chain rule. Well, now we're differentiating with respect to time, dt. So anybody that's not a t is going to need a chain rule. So the derivative of x squared is a 2x dx dt, because I'm not differentiating with respect to x, but rather with t, plus 2y dy dt equals 0. And again, that's the one that's going to get you. You're going to forget one of these days. You're going to forget to put a 0 over there. But 25 squared is the number. If you differentiate a number, you get 0. The next part of my DREDSA is to substitute specific stuff. So I look back up at this and I look for essentially usually for the word when, right? So when it is 24 feet from the ground. So 24 feet from the ground would mean that what they're saying is when the thing I called y is 24, right? Because 24 feet from the ground would be the y value. So when I go to substitute in, here's the thing I want you to notice. I know dx dt, right? So when we go to substitute, right, I don't know x. I do know dx dt, right? I know this. It's a 1. Plus 2y, I know y. And dy dt is the thing that I want, right? And I probably should have started with that, and I apologize. Every once in a while I get a little rusty. A very good thing to do at the beginning of your problem is see what they're asking you for. They ask you, how fast is the end slipping down the wall? They want dy dt. That's the answer they want. So the question mark here is, I really need to know what x is in order to plug in, right? So when I want to substitute, I really need to know what that x coordinate is. Well, I'm going to draw a separate diagram over here for my substituting. So this is more of a snapshot. So the thing to keep in mind, right, this is a picture. This is meant to be a video. That's why you need to label the variables as something that varies. But in this moment, I have a triangle that has 24 on one side, 25 on the other, and then some x coordinate. You can use Pythagorean theorem to find that x is 7. There's nothing wrong with that. It is better, so you could have found that by doing the square root of 25 squared minus 24 squared. But if you don't have a calculator, have some fun with that. It's not a great plan. The best plan is to recognize that this is a Pythagorean triple. So I'm going to do a quick, so there are Pythag Triples. You should memorize them. They go leg, leg, hypotenuse. So 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 9, 40, 41. There are others, but to be honest, those are the 5 that come up. So see how I had a leg that was 24 and a hypotenuse that was 25? That's why I know my other leg is 7. It's worth memorizing them. You don't have to, but the AP probably wouldn't make this a calculator problem because they would assume that you have those memorized, and if you don't, then you're going to have to gut it out and figure out those numbers and possibly be wrong. So either way, I get x is 7. So now when I substitute in, I get 2 times 7 times 1 plus 2 times, what did we say y was? 24. dy dt equals 0. Now, I could have also solved for dy dt first if I want. I didn't bother. When I move this 14 over, right, I'm going to get 48 dy dt equals a negative 14. So my dy dt is going to be up. I might cancel the 2. You don't have to, right? You can cancel a 2 out of the 14 and a 2 out of the 48 and get a negative 7/24 feet per second. But that's not the answer to the question, right? The issue here, and that's that last thing in the dread saw, is that I need to carefully read the question that was asked and make sure I answer it. It says, at what rate is the other end slipping down the wall? Well, the reason this is negative is because the ladder is going down, and thus y is getting smaller. But if you want to know how fast it is slipping down the wall, the word down is already taking care of the directional part. It's taking care of the part that's y is getting smaller. So when I answer the question, I would probably say it's moving down at 7/24 feet per second. Because you're not moving down at a negative rate, that would mean that you were moving up, right? So you want to answer the question. So I'm going to erase E1, and then you can try P1. In case you can't see P1, or in case like it's a little bit not big enough, whatever, I think it probably depends on your eyesight. I'm going to read you P1 first, and then you can pause me if you want. So P1, also a ladder problem. A 13-foot ladder is leaning against a wall. If the top of the ladder slips down the wall at a rate of 2 feet per second, how fast will the foot be moving away from the wall when the top is 5 feet above the ground? And then the 5-6 feet per second is intended to be the answer. Some of these problems come with answers, some of them don't. So that's not a huge spoiler because you obviously still have to be able to do the work to get to that spot. So I'll leave the Pythagorean triples there because hint, hint, wink, wink, nod, nod, you should memorize them. So yeah, I'm going to walk through P1. If you don't want to do P1 with me, then you should pause me. So I'm going to draw my ladder going the other way just to prove to you it really doesn't matter which way I draw it. Okay, so I have this ladder. We know that the ground makes a 90-degree angle with the wall. I know the ladder is 13 feet, and that's not going to change, right? So I'm doing my diagram and my rates. Other stuff I know. It is sliding down the wall, so this value right here is a negative 2 feet per second, the rate at which it's sliding. I'm going to call this H this time just to make the point that you really can label them however you want, so I'm going to call that dHdt. And I'll use this as B for base. As that's sliding down, this is sliding out, so dB dt. And I believe dB dt is what we want, right? How fast will the foot be moving? So that's the thing that we want. We want dB dt, right? And that's all we know, right? When the wall, when the top is 5 feet above the ground, we can't plug that in yet because that's very time-specific stuff. That's not stuff that's true all the time. It's true at a specific moment, hence the word when, right? So we don't plug in the when stuff till we get to this substitute-specific stuff. All right, so there's my diagram and my rates. When I write my equation, I am not at all shocked that it is yet again Pythagorean theorem. B squared plus h squared equals 13 squared, right? And when I differentiate, I actually get the exact same thing I got last time, except it's b's and h's instead, right? So 2b dB dt plus 2h dH dt equals 0, right? Now, if you wanted, this is the thing that you want. If you want, you can solve for that now. Like, there's nothing wrong with that. So I didn't do that last time, but if you want, you could solve for that, and you'd get 2b dB dt equals negative 2h dH dt, and then you could divide by the 2b, and you'd get that dB dt is you'd cancel the 2's, and you'd get negative h times dH dt over b. And that's fine if you want. You don't have to do that, but if you want, it does make it a little bit easier when you go to plug in. It's entirely up to you. You can also still just plug into this one, okay? When I go to substitute in, now I'm at a specific moment. Now I'm at the moment where this ladder is 5 feet off the ground, right? So I don't know this b. Well, thankfully, it's a Pythagorean triple, right? 5, 12, 13 is a Pythagorean triple, right? So 5 is one leg, 13 is the hypotenuse. That means the other leg is 12. Again, you could use Pythagorean theorem. Not everything you're going to see is a Pythagorean triple, but a lot of them are Pythagorean triples. So, I'm just saying, it's kind of worth it. All right. So when I go to substitute in, my dB dt is going to be negative h, so that's negative 5, my bad, negative 5. dH dt, which we were given as a negative 2, over b, which was a 12. So I get 10 over 12, which is 5/6. Now I know that b was measured in feet, and t was measured in seconds, so I get 5/6 feet per second. And then I answer the question. When the answer is positive, you pretty much don't have to put a lot of thought into it. You can just go ahead and answer. When the answer is negative, you might need to double check if the question was worded in such a way that you should include the negative with like the word down or the word closer or some other value. So there's my 5/6 feet per second. So we're going to stop this video here, and since we did an awful lot of talking at the beginning, and I'll go ahead and get us set up for E2P2.